So, as usual, we'll be recording the session so that you are aware of that. I have a meeting at 11:30, so try to wrap up today's session probably by 11:20. So depending on the material that we cover, we may have a break, or we can actually, we may also continue till 11:20. So be prepared for that. Okay, so let's start. Last time on Monday, we discussed types, and the last thing that we were discussing was if we need to do a conversion, how do we do this? What do we allow our programming language to actually do in a given type conversion situation? So type conversion is going to come because you will have mismatched types or incompatible types from time to time. So if you know what can be done about it, then you can let that type conversion. If you don't know, of course, then you have other problems. So there are two questions that we usually ask. One is, do we use a code to designate the conversion? Do we have a specific code that does the conversion? If it is yes, then this has to be manually done or explicitly converted. So there has to be some code someone will write in this case. Whereas if you don't need to have a conversion code designated for that particular purpose, you can do this automatically, hence implicitly do the conversion. This is the first part. Of course, the reason that we have a designated code, conversion code, might be that we need data representation changes when we do this conversion. So if the data representation changes, then we have to be careful and we have to make sure that that change is proper. And in some cases, it may be that you don't need to have a change and just a type change would be sufficient. So in that case, you don't need to have a specific representation change. Let's look at an example in Java. So implicit conversion, you can have a representation change. For example, if you are promoting integer to double, there has to be a representation change. In some cases, like in upcasting, which we'll cover later on again, but just to say it here, there is no representation change. So when you do an upcasting, you don't need to worry about a representation change. In the case of explicit conversion, there might be, again, representation change, like going from a double to integer. And in some cases, there may not be actually representation change required, which is the case of downcasting. So when you look at a simple object hierarchy like this one, you have objects, and then you have an extended object, that animal that extends the object, and then another class that extends animals, and then there are two that actually extends mammal and cat and dogs in this case. So upcasting and downcasting will allow building the complicated program using simple syntax, and it will give great advantages like polymorphism or grouping different objects. So this is clear. So in an upcasting case, allowing an object of a subclass type to be treated as an object of any superclass. So this is all clear. This is done automatically This is how Java actually handles it, while downcasting may be manually done by the programmer. Sorry. So there is a simple example here. You have a class A, one simple class variable field, and you have another class that extends A, and you have an instance of A as A1 and A as A2. Now you have another instance of sub A as sub A. Now you can do this A1, you can assign sub A to A1. This is okay, this is upcasting. And you can downcast in this case because of the specifics of actually the declarations here. And you cannot, in this case, for example, you cannot have A2 assigned to sub A. This will give a completion error. You can do this type of casting, downcasting. This will be compiling okay, but there will be a runtime error. And this is a completion error. A1 doesn't have. And then this will be also okay. So as I said, I'm not going to get into details of this one. We are going to cover this probably in several weeks. So just an example that you can have this downcasting, upcasting as part of your typing system. So going back to kind of in summary, what a type system is, we need a type constructor to build new data types based on simple data types that are given to us, provided by the language. Right. So type checking that translates. This is a translator. What it does is it actually checks if a data type is correctly used in whatever context, in an assignment, in an expression, or whatever. So for this one, type checking will require a few concepts to be in place. One is the type inference. You have to infer the type of an expression whose data type is not given explicitly. You have an expression, and potentially the result of that expression is going to be used as a, let's say, as a value somewhere, maybe as an assignment right-hand side, or as a formal as a parameter to a function, whatever, right? So in this case, if there is no specific way that actually, or it's not explicitly clear what the value is of that expression, then you need to do some sort of type inference. Okay. The second one is type equivalence. In this case, type inference is just to make sure that you know what a type is, what the type of an expression or the value is, right? Type equivalence compares two types, two given types, and if they are the same, they can be used instead of the other. They can be swapped for whatever reason, right? Then you have what we call type equivalence. Type compatibility answers the question such that can we use a value of type A in a place that expects type B, right? So the question is, can we use a value of type A in a place that expects some type B? This is not exactly the same as type equivalence. You might have type equivalence might be a subset of type compatibility, but you might have, for example, these conversion rules that actually can extend type equivalence into type compatibility. So you might have this type compatibility could be a larger set compared to type equivalence. Now the question is, how are we going to do this one? This is not a very simple thing, especially when you have user-defined types and anonymous types. We discussed this one earlier as well, because the user-defined types and anonymous types will actually make this equivalency, compatibility, and inference quite difficult, especially if there are recursive definitions. So there are solutions to this, of course, but we have to always consider the possibility or consider what the cost is. Do we have any cost of doing type inference? If the type inference cost is too much, that I am taking, let's say, minutes, or not minutes necessarily, but if I am doing something in milliseconds, let's say in C, let's say a few operations takes maybe a fraction of a millisecond, and you actually add type inference or type equivalence or type compatibility, whatever it is, and especially if you push this to runtime, then those fraction of a millisecond can become a big overhead for your programming language. So because of that, this type checking or typing systems for many languages, they start with nice goals, these nice theoretical, let's say, underpinnings. It starts from there, but when you go towards practical implementations, you start actually making choices, optimize for this or that. So this is very critical. So type checking versus type inference, you have a standard type checking example here. You have a C-style function, integer function f, integer x, and returns x plus 1. And another G function returns the function f with an expression. When we look at the body of each function and use declared types of identifiers to check the agreement. So we can do this very easily. We can say, okay, can we do this one actually? Yeah, this is obviously fine. Why? Let's look at this one here. This requires an integer return, and x plus 1, x an integer. Now we need to make sure that this operator here, this plus operator, we understand this, but most probably the plus operator for our language will be actually when there is an integer, and this literal will be interpreted as integer as well, most probably, depending on, again, the language itself. And then we can make a decision here. This can be done on compile time. Type inference is when we don't have these declared types. We don't have for function, for example, in this case, I don't give you the, I just give you a function like this. F takes an argument x, so the function is a very simple one. So this is f x. As you can see, there is no return type, and there is no type for x defined, and then some code that actually returns this thing. Now, what you need to do is you need to look at the code without type information and figure out what types could have been declared here. So what could be this integer here, or what could be this x here? Now, what you do is when you look at this one, for example, you say, I have a plus operator and a one literal integer. So x plus 1 must mean that if this is a literal integer, then x probably will be somehow inferred, the type of X has to be inferred by this particular operator on that type. Very simple, right? Now, some languages like these are ML is one, and ML is kind of very, let's say, eager about this type inference stuff, and they try to actually design it such that it is tractable. This is not a very easy thing to do, you can imagine. For example, now what I have to do is I have to make sure that, for example, this literal is, so if I can interpret this in two ways, one is, let's say, an integer, another is as a, let's say, floating point number, then this return type here has to be actually interpreted as in two ways as well, potentially. All right. So similarly, the argument to the f function, you have to also make sure that this is actually decided. So the question is, can you do this on the fly, or can you do this hopefully during compilation? Now, the motivation behind types and type checking is type systems have improved steadily since the algol days. They are important for modularity, compilation, and reliability, and of course, documenting semantic of the specific language or specific program that you are writing. Type inference, this is widely regarded as an important language innovation, but just an innovation. So modern languages try to actually incorporate as much as possible of these type of type inference. But again, there are costs associated with inference, and when your cost outweighs benefits that you get, you have to be practical. You have to step back and probably do some engineering choices to make sure that that specific overhead is not hindering your, let's say, programming language to be useless. So in summary, type of an expression is computed in the type inference system, not declared. It doesn't require type declarations for variables, and it finds most general type by solving constraints. So you can think of that, let's say in this case, will be certain constraints right here. You can easily say that. Let's look at this one. So here I can put a constraint graph, for example, say, okay, now I have f. See, let's go back. Let's do this one. I have f. This is my function. I don't know the type of that f. I need to know this one. So f, the return type. So an input type, there is an input to this one, and there is an output to this one, right? And output is dependent on this expression here. So I have an expression of this form that would actually depend. Once I know this one, I can easily decide the f, the output of f. And I have an input as well. Input is an x. Now, if I know the type of x here, then I can know x plus 1, and then I can know the return value of f. Of course, it's not just this one. You have g, so g is also here. G has an input as well, and then you have also an expression which is dependent on this guy here and something, right? So this is, I didn't do a proper graph, but what you can do is you can build a graph of dependencies. Which type is depending on which type, and which expression and so forth. And then you find a solution to this constraints, graph constraint. So this is a well-known problem. Then you say, okay, I want to do an assignment for types of these nodes, and they have I have constraints on those nodes, and these constraints could be cyclic. This is a possibility. It may be that, for example, if I had here and g x plus 1, right? Then I have a cycle that f is dependent on g and g is dependent on f. You can see it here. Now, in this case, this cycle could be a problem. So there are algorithms to solve these, of course, but the expense of that algorithm, again, has to be taken into account. But the advantage of this is very clear. It leads to polymorphism. You have a function, okay, and you don't have any required type declaration, and it does actually, the algorithm is set. You have one algorithm, one function, and it can process multiple different values, types. So this is very, very strong. We talk about cost of type inference. Let's look at this parametric polymorphism for a given function. In ML, ML has polymorphic functions. Declaration has no type information, and type inference is done by a type expression with variables and then substitute for the variables as needed. On the other hand, C++ function, for example, template, can be used similarly for polymorphic purposes, polymorphism purposes. You have the declaration that gives the type of a function argument and the result, and then you place inside the template to define the type variables, and then the function application is that type checker does the instantiation, right? So in this case, ML has a module system with, so there is an example here you can see, and the difference in implementation is quite actually obvious. ML actually, what it does is it compiles this function into one function. So after compilation, you have only one function, one code, and type checker determines how function can be used. At runtime, you call that function, and then the way that you call that function, the thing that you need to decide is, of course, the input arguments. Those type checkers or type inference will know and will actually at least check it, and then if it is proper, it will apply it. Whereas in C++, the template swap is compiled into a linkable format first. There is a code, and then the linker duplicates the code, copies it, and for each type of use. So if you have an integer use, then there is an integer copy of the function. If there is a, let's say, real number or floating point number use, then you compile it into, or you duplicate it into a version with that particular type. Of course, this is easy for ML because ML actually ML reference cell is passed by as a pointer. Local T is a pointer to a value on a heap. You can see it here. This local T is going to be on the heap. Whereas you have to, for this particular thing, you have to actually, this is going to use a stack, you have to be careful. I mean, you have to make a copy of that thing because there has to be a specific stack for when you get into that particular code. So C++ arguments, in this case, they're passed by reference, but local T is on the stack, so the size depends on the type. So you can, when this thing goes into the stack, then you have to make sure that this T, depending on the type, if it is an integer, let's say 32-bit, if it is a, let's say, 64-bit integer, then it's going to be larger. So this difference in the way that the code is generated by C++ actually cannot allow you to actually use the same function. If C++ were to actually take this and put in heap, perhaps then it will be a little bit different. But it doesn't probably worth it anyway. So, in summary, types are important in modern languages. They help us organize and document the program, prevent errors, and provide important information to the compiler. Type inference determines best type of an expression for an expression based on known information about the symbols in the expression itself. And polymorphism is a result of type inference. Single algorithm function can have many types. And overloading is a different thing, if you recall. Overloading is actually, it has a symbol with multiple meanings, resolved when program is actually compiled. So overloading and parametric polymorphism is not the same, of course. All right, so this is the end of the lecture for, let me see, data types. We are going to talk about types again at some point in about probably, let me see, in a week or so. We'll discuss these abstract data types, where we are going to actually go a little bit in a different direction to use some paradigms, abstraction and so forth, to let our language be extendable or more powerful, flexible, to create these type of abstract data types. So this will be the next type-related topic. Of course, types are very, very important. They are not gonna go away. When we talk about object-oriented programming, functional programming, even declarative programming, we are gonna talk about types anyway. So typing system is a very, very important concept in any programming paradigm. So going with this one, let's actually look at one simple case where, let me see. What we are going to do now is we are going to, let me see what happened here. Is this the one? Must not the problem. Okay. Okay. Let's do this one again. Maybe this one. No. What's happening here? All right. So what I'm trying to do is I'm gonna, before we finish the topic of types, we need to look at expressions. How do we actually create values from given values, set of values. So these are going to be expressions. And somehow I don't know what's happening. You don't see my screen, right? What happened here? Come on, give me a break. Okay. If I do this one. And presenter view. Swap this. All right. I think this should be better. So let's look at a little bit into expressions. So now up to now we discussed variables. So now we need to decide. So if you see that typing doesn't still do anything in terms of actual actions. Type still says, okay, this is my value set. These are the operations that I can do on them and so forth. But we haven't started doing anything yet. And it has been, I don't know, like 6 weeks, 5 weeks. And we still don't know what our programming language is doing in terms of control. How does it move? What does it do when it starts? So this question of control, we have to somehow now we are in a place to actually start talking about. So control says what gets executed, when and in what order. This is the basic concept in any programming language. What gets executed? What is done? What is the output? What is the specific set of instructions that will be actually executed once your program is compiled or interpreted or whatever. And the other question is, it's not just what is being executed. We have to decide also when that execution happens, and then in what order. Now, of course, this is, you can say this is obvious, very, very obvious, right? I have an instruction, and that instruction or statement, let's say, and that statement gets executed, that's it. And there is another statement afterwards, and then there is another statement afterwards, and then they are actually ordered in that specific order. So this is the first statement, second statement, and third statement, and fourth statement, and so forth. Now, this type of a control is simply actually an imperative paradigm. It doesn't mean that this is the only way that we can actually get things executed and decide when to do it and in what order to do it. In some languages, we are going to see that, let's say, if this is a statement 1, statement 2, statement 3, statement 4, for example, we are going to see that some languages are going to say that the order of execution doesn't need to be in this order, S1, S2, S3, S4. It may be that S3 is done way before S1. Now, this is quite confusing. What do you mean? I mean, this is ridiculous. It looks like ridiculous, but it's not necessarily, because the paradigm that you are thinking of, or I am actually thinking of right now, is the kind of the dominant paradigm, is an imperative one, right? And when I talk about an imperative paradigm, I say, okay, I know about statements and expressions, and there is a natural order to those in my syntax, very simply, and I can put the semantic meaning of that right away on top of it, and that's it. And then I answer the question where I start, what gets executed, and when and in what order. But as I said, this is an imperative paradigm. This is not necessarily the best paradigm, let's say, programming. We know it, we use it. We use it in C++, no, C, and then we use it in some other languages. But this is just one way of actually doing things. Now, this control things usually put into two specific parts, expressions and statements. So I can actually talk about things being executed. Forget about for the time being when and in what order, but things being executed can be grouped into two major things. These are conceptually easy to separate from each other, and they have very concise impact or concise things that when you say expression, I know what it means to execute an expression, and similarly a statement. Now this abstraction of this control has two more things. So these are the main thing, expression and statements, but we have to have two more things into this, and they come because again this third one is procedures and functions. Now control, you can again imperative in an imperative programming language, you can say your statements and expressions comes one after another, but you tend to group things together and reuse them and so forth. Therefore, you need some mechanisms to actually provide this control in a different way. So blocks of code that actually does something with some input and some output. So these are procedures and functions. So this is important. It adds a third kind of an abstraction of control. Now, the last one is exception handling. Now, exception handling is, we have seen in a few cases by now that no matter what you do, there will be unexpected things during your programming. Your language is going to be out there. You are going to build a language, G++. You put it out there, and people are going to use it. And the first thing is going to be the control. And you have the expressions, statements, and procedure, and so forth. What will happen is that there will be cases where something unexpectedly happens. Now, you need to have a decision what to do. So in this case, for example, if I have very simple, these 4 statements, let's assume that something went wrong here. What is it? I have no idea. There could be a lot of things that can go wrong. For example, you might have a type checking or type inference thing, and you might not have actually be able to decide it, whatever that type is. This is a complicated case. A simpler case would be, even though you know you don't have type checking or whatever, but there are things like, for example, let's say division by 0, that your machine, underlying machine, has some of these functions that we discussed in the beginning that may not actually may not generate, may not be, may be partial, not full. So those partial functions, when you have actually only, when you fall in that specific case, falls into that undefined part, then you have a problem. Now you have an exception. This means that you have to decide what to do about control, because that partial function that you have, when it actually generates that problem for you, you need to make a decision. What do we do? So this thing is handled using exception handling mechanisms. Some people think that this is in programming languages community. Some people think that exception handling is not really part of a programming language, and some others says no, it is, because it has something to do with the control, and you cannot just answer the control by looking at the expression, statement, and procedures and functions. You have to have these exception handling mechanisms in place Otherwise, it doesn't. Your control is going to be broken, and your programming language is not going to be complete. Okay. Good. So let's start with these basic cases where we look at this abstraction of control as an expression and a statement. Again, as we always try to do, these computer scientists, they like to actually put theory around whatever they do. So if you actually can explain something theoretically in math, in a mathematical form, then you don't need to worry about explaining them, because mathematics is a universal language. And if I am talking about set theory, and if you have learned set theory in math, then we are in the same boat now, meaning we can communicate. We don't need to worry about communication problems between two of us, or let's say you and me. Now, in pure mathematical form, an expression is a control. We execute something, and at the end of this execution, you have a block of code, let's say. At the end of this execution, there is no side effect in your state. Now, especially when you think about this as a, let's say, imperative programming language, imperative programming languages actually following the von Neumann model. What you do is you take something, you manipulate it, you store it. So at the end of that control thing happens, that execution happens, what will happen is that you'll have some memory changing. There will be some updated memory. So they say, okay, let's actually separate these two things. Yes, I am probably going to be, let's say, if I do, let's say, A plus, what is this? If I do A plus 10, right? This is an expression. In pure mathematical form, it says, okay, at the end of this execution, I'm going to have a value which will be whatever the A's value is, added by, incremented by 10. Let's say if A's value is 10, I have 20. And once this execution happens, I have no change, state change at all in my programming environment. None of my variables have changed. My stack is the same. My heap is the same. So I can actually dump everything before this expression executed, and after this expression executed, the entire machine, let's say I have 28 gigabytes of memory, I dump it, and then those two dumps before and after of these things, of course, if this is the only thing that is working on that machine, is going to be the same. Now, this is a very important thing, very powerful. This says that, okay, if you have what I'm trying to tell you is that you have you are doing something, you're executing something, but your von Neumann model, your memory model, doesn't change after that execution. So what happens to this value then? 10 plus 10. That value is available to you as an output of this expression. Now, if you dump it, meaning if you don't do anything with it, it's going to be gone. If you do something with it, like what, for example, let's say use it in another expression, or send it as a parameter to a function, or send it as a parameter to an assignment operator, or a statement. So, on the other hand, a statement will always have a side effect. This is the pure mathematical explanation, and there will be no return value. So not necessarily in C, but let's say if I have another in one language, a equals a plus 10. This is not C, this should be something else. Now this is a statement. Forget about this one, this is expression. We know that. And then what we do is there is a value here that is generated. And that value is at the end of this statement. When it is executed, A will have 20. And this statement will not return any value at all. So there is no such thing as the value of a statement, whereas there is a such thing as value of an expression. Very simple distinction, very, very simple. It's like, I mean, so what? This is obvious. It's not that actually bad, because this distinction can actually let you do a lot of different things with expressions and statements. Let's talk about those. Now, most functional languages tries to actually adhere to this specific definition. So they separate expressions as no side effect and return value abstraction versus statements that have side effects and no return value. Now, you can think of that actually, let's say in a functional language, the expressions alone may not actually achieve what you want to achieve. At some point, whatever you do, you have to do some state changes. Therefore, you need to have some statements. Now, when you have those type of statements, then we need to be careful about what functional languages are going to be doing for those type of things. Because when you start actually the statement using statements, then what happens is that this question that we asked, what gets executed, and when and in what order becomes an important thing. Now, if you think about expression, look at it this way. If there is no, if an expression has no side effect and only a return value, okay, there is no side effect. A plus 10, no side effect at all. Let's have another one. Let's say B times C. Again, no side effect. Now, can you tell me when should I actually do these two things? Should I do A plus 10 earlier than B plus C, B times C, or vice versa, or maybe at the same time, or whatever? Since there is no side effect after the execution of this expression, this question of when I can actually run them, in what order, is already become obvious. I can have a few choices depending on what I want to do. And this is not necessarily limited to just a specific order. It can be that, we'll see that, let's say we can do lazy evaluation, meaning we don't want to actually, we may not want to evaluate the value of an expression until we need it. This is a very different concept than simple imperative paradigm. In an imperative paradigm, when you say do this, it is done. You cannot actually say, okay, hey, wait 10 seconds and maybe after this you can do it. No. But in a functional programming language, these type of ordering of the expressions execution could be, you might have more control over them. You might have more possibilities, flexibilities when it comes to in which order you do. Okay. Now, but what I mean, again, we started with pure mathematical form, and then we say, okay, functional languages achieve this. Now hits the reality. The reality is there is no clear cut in most languages. Why? Again, first of all, I want to be able to actually use these concepts, these universal concepts that comes from math. Very nice, because when I actually tell them, you know what it is. There is a universal language that we know, we can learn, and once we learn, we can communicate this. But the problem is there are cases where practicality may take over. So this is a computer scientist perspective. Make everything scientific in a way. Put theory around it. Base everything on a theory, hopefully mathematics, and then you are fine. But engineering part of it, part of us, says, not necessarily. I want to be practical. What do you mean by, let's say, I want to have an expression that can be done, let's say, in any order? Do I really need it? In an imperative programming language concept, probably not. In an object-oriented programming language concept, probably not. And also, most probably, in a declarative programming language, I don't want it. I may not need it. So therefore, what happens is that this clear-cut difference of what an expression and a statement is in most languages is not actually there. So for example, C takes a statement, the assignment statement, and returns a value. This is the kind of the why. Again, practicality. They say once I have assignment, so if I have A assigned to B plus C, this assignment, when it takes place, I have already something in my registers on the CPU available to me to be used. The question is, do I actually just discard it? Or if I'm able to use it, do I use it? And the answer is, again, efficiency. The engineering heads, engineering thinking said, okay, efficiency is more important. If the things are already in a register, then I'm going to use them if I need to. Not always I use them, but why not? Okay, so this clear-cut distinction is not necessarily obvious in many programming languages. So an expression is constructed recursively. You have basic expressions, literals and identifiers. You have operators, functions, special symbols, and you have a number of operands. You might have an operator with only one operand, a binary one, or ternary one, and so forth. You have the operator and function. These are, in this case, the operator and a function in an expression. They are equivalent concepts, and there are different ways of actually writing an expression. You might have an infix notation like this, which we know very well. You can have a prefix notation, like in Ada. You can have prefix notation like in Lisp, and you can have postfix notation like in PostScript. Now, expressions and side effects. Side effect, as I said, shouldn't be there. And side effect is when you change something in your memory, stack or heap, right? Side effects can be undesirable. Side effects are necessary, but in some cases, controlling it is all about, actually programming is going to be all about controlling those side effects. Semantic meaning of your program is going to be actually depend on that. But a program without side effect, it does nothing, as we said. Expression, in this case, since it has no side effect, order of evaluating a sub-expression does not matter, should not matter. Like, therefore, if you have a side effect, then you have a problem. So the question is, let's say, A plus B, let's say, right, plus C plus D. You have an expression like this. Now, if there is no, so this is a recursive, you can see that this is an expression. It's a recursive thing. Starts with, as we said here, you can look at maybe just a moment. Basic expressions, operators, functions, special symbols, and so forth. Right now, the question is, if there is no side effect anywhere during the execution of this expression, what I can do is I can execute this one and then this one, or I can execute this one and then this one. So I can actually have two options here, because since there is no state change, it doesn't matter which one I actually do first. So the order within the expression itself is going to become important if you have a side effect. In C, for example, we have these type of problems, right? So if I have A plus, let's say, B equals 10 times C and whatever later, then now you have a problem. You cannot actually say that A plus B, or the first part of the expression, the left-hand side of this plus operator can be done, or the other one can be done. The other one can be executed first. In this case, since this one has a side effect, you have no choice but make sure that your semantic agrees with this execution of this particular expression. So it is your responsibility. If I didn't have that one, it's no problem. I don't even think about it. Now I'm starting to think about it. So this is the kind of the engineering part of us gets into trouble now, right? So we wanted to have some, let's say, optimization. We wanted to do things faster, more efficient. But then when we introduce this type of a side effect, then our theoretical explanation doesn't hold anymore. Therefore, now we need to communicate this to our user of our programming language. Everybody needs to know this. And you can see, you know that in C, for example, most of these type of details are very important, and we learn them. We need to learn them. If we didn't have this particular thing, perhaps we'll be losing some engineering advantages, but then we needed to learn a little bit less. Maybe, I don't know. Okay. Now, there are two major order of evaluation of an expression. One is what we call applicative order evaluation. Evaluate the operands first, then apply the operators. This is what we call bottom-up evaluation. So what you do is, if you have 3 plus 4 times 5 plus 6, 5 minus 6, sorry, then what you do is you start for each of these operators, take the operator, whatever the operator, okay, and make sure that the operands are evaluated. So in what order? Again, if the order is important based on the definition of this operator, then you may have it, but most probably it's not going to be important here. So you do the 3, evaluate 3, and then 4. Now you can evaluate this specific expression, sub-expression, which is 7. The same goes for here. You evaluate this, you evaluate this, apply the operator, which is now -1. Now, for this guy, you need to evaluate this guy, which is already evaluated. You need to evaluate this guy, which is already evaluated. Then you can take this to be -7. All right. Now, of course, depending on the language, you might have actually these orders matter. So you can see an example here. A simple C code on the left generates, prints out 4, whereas this guy in Java actually is very similar code. You can see it is just x plus 1, and then x is returned. and then you have x plus f here. All right. So the order is important here. C usually does it right to left, so it goes this way. And Java is always left to right, it goes this way. Now you can see the effect of side effect, right? So x is first evaluated here, and x is in the first one is 1, and then f is evaluated. You go to f, you have 1, 1 plus 1 is 2, return 2, 1 plus 2 is 3. Whereas in C, if you start from left to right, right to left, you go for this one first, you get in here, x is 1 in the beginning, x is now 2, there is a side effect, and then you turn 2, and f returns 2, and x is now updated to be 2. So then you have 4. Now if we prevented this side effect, then we wouldn't have any problem. How could we prevent this? Can someone say? I would have done something, and once I have, let's say in C, if I had this type of maybe scope, this shouldn't have been a problem. Global variables, right? So this is the problem here. You have a global variable, and a global variable can be accessed by the different parts of an expression, subpart of an expression, and the effect is going to be actually, since you have a global variable, that global variable is going to be updated depending on which order you actually do the calculation. Right. This is one of the reasons that we don't like global variables. You can see that this is very, so if a pure functional programmer or programming language guy, advocate, will say, okay, this wouldn't have happened if you had actually an expression could not ever generate a side effect. Then I could have done it left to right, right to left, or random order or whatever. Now, let me ask you a question. Does it really matter if I have an expression and the part of the sub-expressions can be, let's say, do I have any advantage of having an arbitrary order in evaluation versus a strict order evaluation? Can someone comment on this one? Would there be any place where this will be useful? If I know, let's say C is, and then you have to be careful here again, usually, this is a very bad thing. We shouldn't have actually in a language, usually is up to open to interpretation. Sometimes it may not happen. Most of the time it may happen, but sometimes it may not happen. Then I have a problem. So the right to left, if it is, let's say, always right to left, and Java says always left to right, okay, fine. Do I have any advantage? Can you think of any advantage of doing this arbitrarily? Meaning I have expression 1, expression 2, these are the operators, and left to right, right to left, this is strict evaluation. And I am advocating for E1 and E2 to be randomly evaluated. Maybe I choose E1 first, maybe E2 first, or vice versa. Okay, the question is, where does this help me? Can you think of any practical cases? Oh, you know, if I am able to actually take these two things, arbitrarily evaluate them, then I will have an advantage. Can you think of any? Anybody? Are we all sleeping? Let me give you a clue. Let's say I want to do parallel programming. I have a machine with, let's say, a lot of CPUs or cores. Can someone say anything now? By the way, are we on? Does anybody hear me? Someone say something. All right, so yes, good. All right, so I mean, I already told you what the advantage could be, right? So if I have E1 and E2, in this case, sub-expression E1 and sub-expression E2 can be done in, let's say, in any order. What I can do is I can tell my compiler, hey, compiler, let's do a funny thing here. I have a CPU here. This is the execution now. I have my first CPU or first core. This is core 1. And then I have my second core, core 2. I put this expression in core 1. I could put this expression in core 2. I can run them and I can combine them in, let's say, in one of those expressions. Now what I do is very simply, because of this simple no order requirement, I can easily schedule these type of, let's say, like parallel programming concepts. So this will be important. There is a sequence operator. This is an operator where you have a set of set of expressions, first to n, and then the return value of this set of expression is for the last one. Now again, this is also a good example. This is the return value. Now what happens is that if you have applicative order, what you'll do is you'll start this one first, this one second, and so forth. This one end. And in that case, you don't care about, hopefully, side effects, because you'll know that since this is the order of evaluation, you'll say, okay, I would make sure that the programmer will make sure that this expression 1 does the right thing for the expression 2 and so forth. And many languages have these type of sequence operators. Now the alternative is non-strict evaluation. You evaluate an expression without necessarily evaluating all the sub-expressions. You don't need it. Now, there are good examples for these type of things. For example, short-circuit Boolean expression, if expression and case expression, like this one. If false and X, then if whatever, right? No need to evaluate X, because no matter what you do, since false is false, the first part of it is already done. This is a short-circuit evaluation. So what is it good for? Of course, you can avoid, let's say, evaluating another expression, which will take time, of course. If expression, Turner operator if is again not if statement but expression. You have if test expression and then expression or else expression. This is also this way. Test expression is always evaluated first. Either then or else is evaluated, not the both. All right. Case expression is the same thing. Now, another way of actually evaluating or let's say defining order in expressions is what we call normal order evaluation. So when there is no side effect, a normal order evaluation can actually take expressions, evaluate them in mathematical form. And operation evaluated before and the operands are evaluated. Be careful here. Just a moment ago we said we would do actually bottom up, meaning the operands will be evaluated before the operators. Now, the normal order evaluation says, no, you don't need that. You need to actually evaluate your operation first. If you are doing, let's say, A and B, right? First do this guy. This is what you want to do. You want to do an AND. Now the question is, for this AND operator, what do you need? You need a left-hand side, a right-hand side. And then you can decide if the left-hand side is already a false one, you can dump it, dump the rest of it, and so forth. So operations are evaluated before the operands are evaluated, and the operands are evaluated only when necessary. Very simple. This is not top to bottom, not the bottom up. Like you have an example here, right? So applicative order square double 2 would mean I will have when I actually have 2 here, double 2 comes here. Now it says, this guy says 2 plus 2 is 4. So I have to do bottom up. Normal order evaluation is going to say, okay, double 2, I do plus x plus x. I need to worry about the plus. And I need to only evaluate it whenever I need to actually get this value. I need this value specifically, whatever that value is. Like here, you see in this case, it doesn't evaluate till it actually comes to here. All right. We are going to talk about this lazy evaluation or normal order evaluation when we discuss functional programming paradigm again. So for the time being, I'm going to go to assignments. There are central constructs for imperative languages. Functional languages, you have to be careful. General syntax is actually you have a target variable, assignment operator, and expression. Okay. Conditional targets you can have. Declaration order is important. Binding is important. You have to decide all these things. You can have compound operators, assignment comparator like a increment and you know these type of things. Doesn't matter. You might have unary assignment. Unary assignment operators are in especially C-based languages combine increment and decrement with assignment like plus count, for example. In some cases, you can have assignments and expressions. You can have multiple list assignments, and you can have statements, if statements, for example, case switch statements and loops and so forth. So this is these are the two basic controls that we discuss, and we are gonna talk about next. Let me see what are we gonna talk about next. Exceptions and then procedures or functions and procedures. Okay. Any questions? If not, then let's stop here. I think, again, exceptions I will cover in 1.5 hours or so. So next week we'll be probably done with procedures. So lecture 6 and 7, exceptions and procedures will be completed next week. And then we'll have the ADT and then prologue and then functional programming and object-oriented programming afterwards. All right, so thank you for your interest. I'll see you hopefully on Monday at 2 o'clock. Have a nice day, everybody.